Welcome, ladies and gentlemen, esteemed viewers. I am Timur Abbas, and it is my pleasure to welcome you all to IEEE VTS Young Professionals webinar. As you know, this platform serves as a beacon for nurturing the talent of young professionals, and we provide them a platform where they can come and talk about their ongoing research, their academic achievements, or their experiences. So the whole idea is to give them an opportunity to present themselves. And today we are honored to have Dr. Ferheen Ayaz, sorry, a distinguished research fellow at 60 Lab, University of Sussex. Uh, she will be talking about smart energy management and optimized uh, Prosum for achieving dynamic net zero balance. Without further wait, let's extend a warm welcome to Dr. Ferheen and learn more about the topic from her. So I would like to invite Dr. Ferheen. Welcome.
Thank you, Tamu, for giving me the platform to present my work. So I would like to begin with introducing myself. I'm Ferheen Ayaz. I'm working as a research fellow at 60 Lab in University of Sussex, and I have completed my PhD in 2022 from University of Sussex on the topic of connected vehicles and securing messages in connected vehicles through blockchain. Then I completed my first postdoc at University of Glasgow, where I worked on the security of machine learning on edge devices. Here I'm working on smart energy management. The title of my talk today seems a bit long, but in short, it is about how we can utilize electric vehicles for bidirectional energy transfer. Like they can sell their energy if they have, and they can consume whenever they require. So, that my topic is how 6G communications can play a role in achieving net zero and balancing demand and supply. So that's what I'm working upon. So today uh, we will be talking about my recent work that has been submitted in IEEE transactions on a smart grid. um, I will begin with what I will be talking about today. So I will begin with introduction, which will include motivation, why we have chosen this topic, and what are the objectives of our work. Then I will explain the recent work about energy management system, including what's the architecture is and what AI models we have used to predict energy, and how we are balancing demand and supply, the optimization problem that we have worked upon, and some incentive distribution for electric vehicles. This will be followed by results and then conclusion. After that, I'll be ready for your questions. Let's begin with the introduction. So, as we know that the number of electric vehicles on road are rising, this is mainly because to achieve net zero and employing electric vehicles on road is definitely a positive step because they do not produce harmful emissions. That's why the world is moving towards electric vehicles. But this is associated with a big challenge of greater energy demand. So the transport electricity demands are rising day by day, and at the same time we want to move towards renewable energy, because when we talk about zero emissions and we want zero emissions through electric vehicles, and then we provide energy to electric vehicles through fossil fuels, then that won't achieve our target, because fossil fuels will ultimately result in high carbon emissions while generating electricity. So we have to meet the demands of electric vehicles, at the same time meet them through renewable energy resources. And that's what our main challenge is, because when we talk about energy resources in terms of renewable form, for example, solar energy or wind energy, they depend upon many parameters. For example, weather parameters, the wind speed, wind direction, or solar radiance. So we do not expect a, a stable supply from them. There can be unstable supply and there can be fluctuations. And also, right now, we don't have a very massive and very well established infrastructure of renewable resources. So, when we want zero emissions from our electricity source, one big challenge is to change the whole infrastructure of electricity generation system, and that will be very costly. So, one of the solutions to reduce cost and meet the demands in environmental friendly way is to employ the use of distributed energy resources. And here comes the peer-to-peer energy exchange. So when we talk about distributed energy resources, it doesn't mean that we need a whole power plant for solar energy. Let's say we have a house and which has a solar panel at the rooftop. Then that house can consume the energy from the solar panel, and if it has some remaining, it can distribute it to others. So, and it can distribute it directly to the electric vehicle. So that's what peer-to-peer energy exchange. And when we talk about peer-to-peer energy exchange, then we come across the term prosumerism. So and that's an evolving term, quite new. It means that the energy consumer can also become the energy provider. And here the biggest example is electric vehicle. The electric vehicle is an energy consumer itself, but let's say it has some energy left in it at night and it does not have to travel, so it can sell this remaining energy stored in its battery storage system to another consumer, and in exchange of some monetary incentives, or maybe just to help someone. uh, yes, then it will have to buy energy for itself later on. But what it can do, it can buy energy during off peak hours, and then it can sell it during peak hours. So in this way, it can also earn some profit as well. So energy from electric vehicle can be transferred bidirectionally, because we have bidirectional charges available. So it can either give back energy to the grid, or to another electric vehicle, or maybe to another consumer like a house or a building. Because it can travel, then it can go to any other consumer itself. In this work, and overall for utilizing prosumerism, we have many objectives. The first one is grid load reduction. So when electric vehicles will help in energy supply, so basically the production of electricity generation load on the main grid will reduce, and ultimately it will lead to the cost reduction, because the grid will have to pay some cost for electricity production. And then we also aim to increase the utility of electric vehicles themselves, because they can buy energy during off peak at cheaper prices, and they can buy energy from another electric vehicle, and maybe they have to travel less towards another electric vehicle rather than to a charging station. And then we achieve prosumerism. In that's being cooperative in the society, and then by selling energy, prosumerism does not only lead to monetary profit, but also it has some altruistic goals as well. Because when we will sell energy, then we will think that yes, we are somehow contributing towards the environment, we are selling clean energy, and we are helping the community. And obviously environmental considerations are one of the objectives. And in this work, we have proposed to put penalty on grids for carbon emissions. Like if the grid is producing energy through fossil fuels, they will have to pay a penalty for carbon emissions to some regulatory authorities. That's what we are also considering in this work. Now we'll move on to the proposed energy management system that we have so far formulated. Here we consider a transportation network, and here we have also considered three type of electric vehicles consisting of a car, a bus, and a lorry. They have different battery capacities and different aerodynamic properties like the frontal area and the size of wheel, which really matters when it comes to energy consumption. And this transportation network is powered by distributed renewable energy resources. We have considered the wind resource and the solar resource. But obviously, this power is not enough to power the whole transportation network when we have large number of electric vehicles. So the rest of the power is supplied by the main grid. And we have some uh, machine learning models incorporated in electric vehicles. What they do, they um, uh, predict the demand and supply of vehicles. When a vehicle start its journey, then depending upon the route, it predicts how much energy will be consumed in its journey, and depending upon the energy consumed and the current state of charge, they decide whether they will need some energy on their way and what will be the location where they will be stopping for charging up. Maybe they don't need any energy, they have enough in their battery, and they can complete their journey and still left some so they can sell their energy to electric vehicles. So this whole information, whatever they predict, they send to 5G aggregators. Here we are talking about a transportation network that is powered by 5G communications, and the vehicles can talk to the aggregator, and aggregator then send the information to the main grid. So basically, the aggregators send hourly predictions of demand and supply from the electric vehicles that it is anticipating, and the hourly prediction of supply from wind sources and power sources is also sent to the main grid. Then the grid decides how much energy it needs to provide to the transportation network, depending upon how much it's getting from the distributed sources, and what's the demand and supply from electric vehicles. So it optimizes its cost. It tries to minimize its cost and optimize the supply. Uh, Here, we will see how the problem is formulated in the upcoming slides. So first, we predicted the output from wind and solar resources. We have different data sets for wind and solar energy sources. Mainly, the parameters for predicting weather related, like time of the day. Is it morning or afternoon or night? And day, maybe it's uh, a winter month or a summer month. And then the other parameters like wind speed, wind direction, and precipitation, solar radius, etc. We used some machine learning models for prediction. They are open source models. Mainly, they are regression models like CAT boost, and then gradient boost, light gradient boost, and hybrid LSTM, that is long short term memory and convolutional neural network. In the results section, I'll show that how the performance of these models vary according to the training time and the accuracy. For predicting energy demand and supply, we have used the same machine learning models, but before that, we performed some mathematics to see how much energy is consumed. So, depending upon the speed of the electric vehicle, its traction force is calculated. What's depending on the speed, acceleration, the mass of the vehicle, and its frontal area. These uh, parameters calculate the force that is required for moving the vehicle, and then what will be the energy consumed. Secondly, we considered the state of the charge, like what's the current uh, battery filled up in the electric vehicle. We consider it as a random variable following log normal distribution, and then what's the state of the charge and what will be the energy consumption. These two parameters decide whether the vehicle will be demanding something during its journey, or maybe it has enough um, currently left in its battery and it can give some of the supply to others. Then we perform optimization. The main goal of our optimization is to achieve the net zero balance. Here, by net zero balance means that we should have enough supply that caters the demand of the transportation network, and the supply is coming from the grid and wind and solar sources, and some of it is coming from electric vehicles who are willing to give their energy, and the demand is coming from the electric vehicles. Based on that, we formulated a problem and then solved it using mixed integer linear programming branch and bound method. And in the problem, we aim to minimize the grid cost um, by optimizing the supply from the grid and the supply from electric vehicles. Like it takes supply from electric vehicles and produces some of its own so as to achieve the minimum overall cost. Then we have some constraints like there is an upper limit on how much a grid can produce, and if it is buying from electric vehicles, then we have to make sure that electric vehicles utility is greater than zero, so it's in the end it's earning some profit. And also, last but not the least, uh, the main concern is to achieve the demand supply balance in the transportation network. And we solved it using branch and bound method. Talking about the cost, I would like to first present the incentive distribution system that we have formulated for electric vehicles. So, when electric vehicle is supplying some energy, and the grid is also supplying energy, what the grid has to pay, the grid has to spend some cost in producing the energy that it's producing itself, and if it is producing from fossil fuels or maybe from any other resources, there's some amount of carbon dioxide that is emitted. In fossil fuel, the amount is greater, but in other resources like solar energy and wind energy, there's a smaller amount that is being uh, emitted. So, whatever the amount is being emitted, depending upon its mass, it has to pay a penalty charge to regulation authorities. Then, if it is buying energy from electric vehicles, so it will pay some price to the electric vehicles proportional to the supply that is being provided. Also, when it comes to electric vehicles, it earns some profit from the main grid and some profit from the regulation authorities. So we have proposed that regulation authorities should also give some profit to electric vehicles so as to encourage prosumerism. But also it had to pay some cost while acquiring the energy that it's giving away, and when it's moving towards a buyer or towards a grid or a charging station, it will be spending some energy, so there's the travel cost associated with the electric vehicles. So that was our proposed system and incentive distribution. Now let's see the results. These are the results of the AI models that I discussed, that we used AI models to predict the solar output, the wind output, and the energy consumption from electric vehicles. So we compared four models: CAD Boost, XG Boost, LGBM, which are available open source in Python, and the hybrid convolutional neural network and LSTM. Like it's the combination of regressive and neural network models. So we see that in terms of training time, the CAT boost is giving the lowest training time, and the lowest training time is lowest computation. So when the computations are low, so obviously it's energy efficient. Secondly, when we talk about its accuracy or the final test error it's giving, it's also low, or sometimes even if it's not low, it's at par, the lowest. Like it's quite considerable. So we used cat boost in the rest of our results. Here, you see the utility of electric vehicles. So it depends upon the price that a grid is paying to electric vehicles for providing energy, and definitely the higher the price, the higher the utility will be. For some of the price, we see that the utility is either zero or negative, and in that case, the electric vehicle will opt not to share its energy if it's suffering from loss. So, um, depending upon the utility, we get the average number of sellers that are here to provide the energy. And the utility does not only depend upon the price paid by grid, but also the traveling distance that it has to make to reach the buyer. So if the traveling distance is high, you see there's a drop in the utility, and this drop in utility will ultimately lead to the drop in number of suppliers. Depending upon the number of suppliers, here we also came to a result of optimum number of charging stations in an area. Um, in these results, we have considered a 20-kilometer long highway consisting of three lanes, and the we assume the charging stations are uniformly distributed across the highway, and then we observed by increasing the number of charging stations, how many number of suppliers and demanding EVs we can receive. So obviously, when there are more number of charging stations, then the vehicles per charging station will be reduced. But when it comes to sellers, we have this optimum number, like the highest number of sellers are at three charging stations rather than two, because uh, if there are only two charging stations in an area, the sellers will have to travel further away, and then their utility will decrease and they won't be able to sell their energy. So that's why we came to an optimum number. So we want more sellers per charging station, because in creating a whole charging station, we have to pay some infrastructure cost. So if we have more number of sellers in a charging station, so that will be the most efficient utilization of an infrastructure. The next result shows how much energy we can avail from electric vehicles. Although they have surplus enough available, for example, with 500 vehicles, we can have around 1 megawatt hour of surplus energy, and with 1000 we can have around 2 megawatt hours. But we cannot avail all of them, as you have seen in the previous results, that it also depends upon the utility of electric vehicles, which relies on the price. So depending upon the price that is being paid by the grid, we have an optimum number of uh, uh, on an optimum price that should be set by the grid to attain the most of the supply from electric vehicles. That's also because if we increase the price, obviously the electric vehicles will have more utility and they will be willing to supply energy, but the overall grid cost will reduce, because if they are paying more to the electric vehicles, they will have to we also have to minimize the grid cost. So we have to have the balance between the cost and the prosumerism availability, and supplying energy of the grid as well. Again, if we look from the perspective of the source of energy, we see that a grid tends to avail more from electric vehicles when it is producing from fossil fuels. This is because the grid has to pay some penalty charge uh, for producing carbon emissions. So instead of paying a high penalty, it will try to avail the energy from electric vehicles. Now, these results show how electric vehicle types like car, bus, or lorry, which of the electric vehicle can result in more demand and supply. And we see that the bus gives more demand as well as more supply, and that's probably because of its parameters like the battery capacity. We have considered its the battery capacity of bus as the highest, that's 320 kilowatt hour, so it can store a large amount of energy, and that's why it has also it has to demand a large amount of energy to charge itself. Now, this plot show how we have achieved reduction in grid cost. So without optimization, the grid will supply whatever the constant it can supply, and with optimization, you see that the cost is approximately half. And this red line is the proposed framework that also considers supply from electric vehicles, and this dotted line considers only optimization, not the supply from electric vehicles. So when we take some supply from electric vehicles, there is a further reduction of 5.3%. Finally, we have achieved net zero successfully through the proposed smart energy management system. You can see in this plot, if we don't optimize, the grid will provide constant supply no matter what the demand is. So that will be the wastage of supply. But when we have very high number of electric vehicles, the demand will be higher than the supply. But with optimization, the demand and supply will be nearly equal. However, if we are talking about optimization without consumerism, there will be a time when the supply will be will not reach the demand, when the demand will be very high with very large number of electric vehicles. So that's why uh, to have the balance, we must need some help from the EVs. So yes, that's our result. That was our last result. Now, I would like to conclude my presentation. Here, we have presented a smart energy management system, and that is orchestrated by 5G aggregator, because 5G communications plays a major role here, because that's the early prediction of demand and supply, and when the grid is continuously getting the prediction information to communication, only then the optimization will be performed. And then we see in plots that the prosumerism, all the contribution from electric vehicles depend upon a number of factors like the price it's getting in exchange of energy, or the distance it has to travel, and also uh, the type of electric vehicle it is, either it is a bus, car, or a lorry. So that was my presentation. Now I am ready for your questions.
Thank you so much. Thank you, Ferheen. It was a pleasure to learn some new things. I mean, we look at the technology in a different way, but in terms of energy optimization, that is another way of looking at it, and I think it makes a lot of sense. So, I mean, we have a couple of questions, and before taking that, I would like to ask or clarify for myself. Uh, we are talking about, like, energy management systems. So who is going to be the manager? Is it the mobile network operators? Is it the service operators or service providers? So who can potentially be the manager for these management systems?
Yes, so here we have assumed that the regulation authorities, maybe the government, because it will impose some penalty to the energy producers for carbon emissions, and it will also provide some incentives to the electric vehicles. Um, Here we have assumed the government, and there's also we have worked on some more peer-to-peer energy exchange, including not only electric vehicles but also some immobile prosumers like houses, buildings, and there we assumed a consortium. We worked on blockchain, and there was a consortium for controlling like the charging stations and the electric vehicle manufacturers, and combined with government authorities as well.
Hmm. So, because I mean, here we can look at it in two or three different, or break it down into two or three different parts. So, one is the regulator, that is what we call government.
Yes.
Then we have the manager, or the service provider. So that can be an automotive company, or whoever is managing the electric grid. Because what we talk about the incentives, so penalties or incentives, of course the regulations may come from the government, but the penalties are enforced, or the benefits, or the what do you call it, the gain that is given to the end customer, I think it will be given by the grid managers. So in terms of, like, maybe you get a cheaper rate for the next time, for the electricity consumption if you have used less than the average, or if you are using more than the average, maybe you are charged more than the average. So in this way, these rates and all these benefits or the penalties, they may come from the grid managers. That's just my understanding. Then we go into another question, that is, like, how this is going to be connected with the telecom network, in a sense that, uh, could this be integrated with the telecom network, so you could monitor it live, how it is, or it may be, and there is an application, just you use the application and do it. So I mean, did you think on the application side of it or not yet?
Yes. So in this work, I have only shown the base stations aggregators, or maybe the edge computing nodes or edge servers. They receive the information from electric vehicles and then pass it on to the grid. So that's the communication role. But we have some other work as well, and we are thinking to regulate it more. For example, um, when electric vehicles are communicating some information, then there could be some security issues and privacy issues. So we will have like the smart meter with the
Hmm.
vehicle, which will directly communicate with the aggregator, so that we don't have uh, like we can reduce the selfish or malicious behavior. If a vehicle is exchanging energy to another vehicle, they cannot lie about it. If they have a smart meter and regulated by smart contract and the blockchain, which is storing the transactions.
Hmm.
So yes, the
Yeah,
when
I mean,
we uh,
it,
I would
it's
like to
quite
say that
quite
when
a
we
wide topic, I agree.
sorry, yeah. So if we are going to implement it, so there will be many things associated, and we'll have to look after for security and communication. So yes, it cannot happen without communication.
Yeah, yeah, definitely, definitely. No, but it's a very interesting area, and I think there is a lot to be done, because we are into electrification of vehicles. We are into 5G and 5G advanced, and soon it will be 6G, that we may see in another decade or so. So there is a lot to be done, and it's fascinating to see. How we need, I mean, the energy consumption and consideration on how to save on the energy, that is also one of the key aspect of it.
Yes.
So thanks a lot. It is a pleasure to have you here on the IEEE VTS Young Professional webinar. And I would like to ask all the viewers, if you are working in the relevant area and have any questions or would like to collaborate, maybe you can directly reach out to Dr. Farheen. Uh, so in the description, we will provide the link to her university profile, so you can look at other work in detail and reach out to her if needed. Any other message, comment from you, Dr. Farheen? If not, yeah, thanks a lot. Thanks for watching, and until next time, see you.